And it's wonderful to be here, and I'm happy to be able to address everyone today, including all the people who are joining online. So as we heard in the beginning, we had quite a few signups, and we're actually still getting signups during the event. So I think we've had about 10 or 20 people sign up just since we started this morning. So hello, everyone. And again, my name is Kenneth Witwer. I'm just going to share my screen here. And my assignment today is to tell you a little bit about detection methods for EVs in blood. So we've heard about blood itself, we've heard about the EVs and the other things that can be found in blood. And now we're going to talk about some of the ways to detect the EVs. So if I may start out, though, by just emphasizing some of the topics that we've already gone over. I recently had the privilege to see some of the 2022 Major League Quadball Championships. So some of you may know this game. It's also called Muggle Quidditch. So the championships in the U.S. this year were held in Howard County, Maryland, which happens to be where I reside. And it's an interesting game that's based upon the Harry Potter series. And so you have these hoops, and you throw the balls through them. But strangely enough, you have to also carry a broomstick between your legs, and so you see how silly this looks here. But I thought these championships actually have a little bit of similarity with the EV studies that we're doing, because it is a full contact sport, and there are some nomenclature disputes. So some people call it Quidditch and others Quadball. But in the end, what everybody is trying to do in this game is the same thing that we're trying to do, which is to get that golden snitch, the EV, out of the population of all the other things that might be in the blood. We could call this the quest for the golden EV. And so my talk is going to be divided here into a few segments. One is on separation, or even the question of whether separation is needed. So we heard about how these different factors can actually be quite important for the function of EVs, even for the survival of EVs. I'm going to talk just a little bit about some of the bulk detection methods that we have and some of the considerations that we know we must take into account when we're working with bulk characterization methods. Then my third chapter is going to be on single EV characterization. I'm just going to give a few examples here because there are many technologies, many methods that have been developed, and many that are being developed right now. And then finally, I'll talk about some of the things that, or actually just show you a slide on some of the things that we can't go over today. We just don't have the time to talk about all of these things. But that's going to be my presentation. So I just want to start out by emphasizing again that extracellular vesicles are just one of the many types of extracellular particles that can be found in blood. And we've heard about these other ones, ranging from the very small proteins, where we could even have a conversation about what to call these proteins. Are they soluble? Are they actually particles themselves? You know, it depends upon your separation method of whether you might consider them to be particles or not, all the way up to these gigantic particles like the big EVs, the big chylomicrons. And unfortunately, all of these particles have something in common with each other. So there's no single characteristic that you can use to separate them from each other. And that's part of the problem with our characterization. And so I often show this slide on where's Wally. As we say in the States, there are different names for this character in different countries in the world. But this might be actually sort of a 1 in 100 kind of case, where you have this character, you know, with a very characteristic outfit on, and you have to find that character on a beach that's full of other people. But this is 1 in 100, and maybe what we're really talking about, as we saw with Dr. Buzesh's presentation, is a more you are here kind of thing, where you're looking at the world, the Earth, in the context of the Milky Way. So more of a 1 in a million or 1 in 10 million scenario. And so the question then becomes, do we want to actually separate our EVs from all these other components, or do we not? And there's no simple answer here. In our EV separation approaches, and I'm showing here a slide that comes from a very nice snapshot that was published in Cell by Clotilde Thierry and her group. So you can see some of the different EV separation technologies here, the different EV separation methodologies. And there's no one method that can be recommended over another. It's simply a matter of determining the method that is best for what you're trying to do. And so everything is possible. We just want to keep in mind where our EVs are going to fall out on this matrix of recovery. So how much of the material do you get back at the end versus specificity. So does it matter to us whether we have a bulk population of EVs with a lot of other things, or do we really need to have those very pure EVs? And of course, the answer to that question is going to depend upon what we're trying to answer. Some of you may have seen the Spider-Man movie where Kirsten Dunst's character says, "Tell me the truth, I'm ready to hear it." And Tobey Maguire says, "Well, you know what? Your $400 exosome isolation reagent, it's just PEG." I'm not making fun of any particular technology here, but we do have to keep in mind of what our technologies are achieving. Now that we have our EVs, maybe we've purified them completely. Maybe they're still in a mixture of many other things. What are we going to do to measure these EVs, to detect them, to understand what they're made of and what else is there? So we can do some total particle measurements. We can look at the total amount of protein or lipid or RNA or really any molecular component of the EV preparation. Sometimes we look for specific components. And so a method that you'll see in a lot of papers, of course, is the Western blot. And so the Western blot can look for one protein or one epitope at a time. And in the case of the Western blot, as for any other affinity reagent methods like in ELISA or like flow panels, we want to remember that we would like to look for both the EV enriched markers, but also those depleted markers, or just the markers of the non-EV populations. I'm showing you here over on the right the results of a panel. This is actually the panel from Miltony that's called MaxPlex. You can look here at different EV epitopes. These were designed. This panel was designed based upon blood EVs. So a lot of the things that you would detect in a blood population. It's always good to understand some of the range of the markers that are involved in your study. And then, of course, also with a bulk preparation, so we're putting everything all together, we can do omics. We can look at what DNA is present, what RNA is present, the transcriptomics, proteomics, lipidomics, metabolomics, glycomics, and so on. And so whether we're looking at single markers or whether we're looking at a broad range of markers, we do want to keep in mind what is present in the EV, but also what is present elsewhere. Here is just a figure from a paper that was recently accepted from my group where we looked at a cell source of EVs. What EVs have come from this particular cell type and what can we detect there? And so we used the EV markers CD63 and CD9. We also looked at the luminal marker TSG101, but we looked at a cellular marker as well. So something that would be deeper in the cell that is less likely than these others to be incorporated into the EVs. Well, that's well and good for a study where we look at cells and their EVs. But what about blood? Does this Western blot really, this approach really tell us anything about what we've isolated from blood? And so in the case of blood, yeah, we might want to look at calnexin or GM130 or some of these other popular markers of cells, so of cellular contamination. But maybe more important in the blood are some of the markers that Dr. Buzesh mentioned and that Dr. Newland mentioned in the beginning, such as the apolipoproteins, the albumin, the immunoglobulins, and the components of some of our other protein complexes, including ribonucleoproteins. Along the way, of course, we're going to be guided by the principles that are laid out in MISEV, and this is from MISEV 2018, and of course now we're in the process of upgrading MISEV to a MISEV 2020 something, and that process is ongoing. All right, so now, to look at the single vesicle, though, to understand all these different sources of EVs in the blood, we may have to go towards single vesicle characterization. And the canonical method for single EV characterization is electron microscopy. This can be transmission, it can be scanning, it can also be cryo-EM. And it would be nice if all of our populations behaved like the bead populations that I'm showing here. So polystyrene beads or silica spheres, where we have very uniform particles. Maybe we have a mixture of particles, and we can see how well the manufacturer has actually made them. Unfortunately, in vivo, Ex vivo, we have a different situation. And so, of course, we've heard from Dr. Buzesh, this is a paper from a group from 2016, on how EVs and lipoprotein particles associate with each other. And this association may be a relatively tight association. And so again, even though we can see the single EVs here, we can also see the things that are associating with them. What about some of the other technologies that have come along or have been recently applied to EV studies? So I'm going to give just examples of 4 technologies here. These are not the only technologies, and I want to stress that I'm not endorsing any of these technologies in particular. But let's start out with nanoparticle tracking analysis. This is also known as single particle tracking. This is an optical method. So here is an example. I'm showing a slide here from Particle Metrics, who have also sponsored this meeting. So what we have here is a laser that is shining through your suspension of particles, and you can track the particle from one frame of a video to another. And then you can determine the size of that particle based upon its Brownian motion. And so there can be a count that comes from this. There can also be a size profile that comes from this. And so we can look at those individual particles, including using fluorescence. And so there's fluorescence that's available for many of these platforms right now. And I think the platform manufacturers are also developing methods where we can look at more than one channel at a time, so that we can get real multiplexing here. Another method that is commonly used is resistive pulse sensing. Now, this is an electrical method. This is the so-called Coulter principle, named after another Wally, Wallace H. Coulter, who invented this back, I think, in the 50s. So this is an old technology, but it's a has a very nice application to measuring EVs. Just a few of the available platforms over on the right there. And this uses electrical sensing. So basically, there's a pore. When the particle passes through the pore, it occludes the pore, and then you are not able to, or you have a fluctuation in the signal that's received. So this will provide you with the real-time size, and then, of course, with each of the events that occurs, you can count up the number of particles and get a concentration. Another platform that's out there is called Single Particle Interferometric Reflectance Imaging Sensor, or SP-IRIS. This is a mouthful, but what it basically does is interferometry to understand how many particles are there and how big they are. And then you can also add fluorescence. So an example of this would be the NanoView ExoView. This is now part of Unchained Labs. And this is how it works. So it's a protein array. You have antibodies that are on the surface of this silica dioxide chip. And the antibodies will capture particles in your population that are positive, that display a particular antigen. Then you can come in after first of all doing an interferometric measurement to again understand the size, the number of the particles that are captured by each spot. You can come in then with fluorescently labeled antibodies or other affinity reagents, and then understand what different antigens are on the surface of the particle that was captured. And so again, this is a true single particle phenotyping technology. And currently we can look at about up to 4 different antigens on these particles. And then finally, of course, we have the whole constellation of flow methods. So flow cytometry now being applied to much smaller particles than cells. And so an example of this is it comes from NanoFCM, the Flow Nano Analyzer. This is a flow platform that has been adapted in particular for small particles. I think we're going to see more of these coming along in the next few years. But here the innovations are that the sample stream is much smaller than what you would have for conventional flow cytometry. In addition to this, the instrument uses gravity flow rather than pushing everything through the channel at pressure to try to get maximum events. Instead, you're trying to slow things down so that you can integrate the signal a bit more and capture some of these dimmer events. Of course, again, with the sample stream being smaller, you have less background. And so this allows you to actually detect some rather small particles. And so in a paper that my lab published last year in JEV, there are several such comparisons that are out there that I would encourage you to look at. But what we looked at were how these different platforms performed for both synthetic particles and then also for EVs. And so we were able to compare them a bit. I don't say that we made the ultimate comparison. You would, of course, want to compare some of these technologies for yourself to see how they work in your hands and for the material that you are working with. But we were able to see that there are some differences in these platforms. And in fact, they're quite complementary to each other in many cases. And so, for example, NTA, when we were evaluating it, there were some fluorescence applications, but I think there are many more that are available now or that are becoming available. Similarly, for RPS, at the time, there was nothing that was available for fluorescence or for phenotyping, but I think that's going to be changing in the near future. SP iris and fluorescence, we've seen more and more reagents that are being developed for this platform, and also with the flow platform, which worked very well to actually discriminate smaller sizes of particles. This is also something that a lot of development has gone into, and that I think more of the flow cytometry companies are paying attention to now. So really looking forward to seeing how these different platforms are developing, but they're not the only ones, right? And we also want to remember a few things as we look at these platforms. We want to remember that in many cases, the platforms are detecting particles, so not necessarily EVs. You will detect that particle as it goes through the pore or as it sits on a surface, but you don't know whether or not that particle is an EV unless you're able to do something else, some sort of a stain. And one of these stains might be a lipid stain, but we again want to remember that lipid dyes will stain other particles, not just EVs. They will also stain lipoprotein particles in many cases, and some proteins. So there are some proteins that seem to have an affinity for these particles. And then finally, even if we do some kind of affinity reagent-based phenotyping, we must keep in mind that there are some surface proteins on EVs, even some of the tetraspanins, that can be cleaved and that can then associate with other particles. So just because we have a tetraspanin positive particle, an integrin positive particle, et cetera, that doesn't necessarily mean that we can conclude that that particle is an EV. So just to keep all these things in mind. Finally, there are many, many platforms that I did not discuss here. And so I apologize to all the people out there who are working on technologies that we wouldn't have the time to go over today. One of these that we're particularly excited about is the AF4 technology. So this is asymmetric flow, field flow fractionation. So instead of saying AFFFF, you can just say AF4. And this is a combination of a separation technology and an analytical technology. So the separation is the AF4, but then you can put detectors downstream. The illustration here on the upper left-hand corner is an example of where a postdoc in my lab, Alessia Gololobova, put just 20 microliters of blood plasma into this separation technology and was then able to see how it separated the different sizes of particles in the blood plasma, including separating things like HDL from the argonaute-containing complexes, separating LDL from VLDL, and so on. A lot of potential, I think, in this technology, and in adding input downstream of the separation to understand what is in our sample. Raman spectroscopy and other vibration-based methods, I think, are coming to the fore as well. And we're hearing more and more about them and how they can provide a fingerprint of EV preparations, help us to really understand some of the differences between the preparations that we make. We heard about the EV corona, and of course, in addition to the EV corona, we have all the other kinds of cargo. So I like to show this illustration of the different vehicles that have been loaded up or have been associated with different cargoes. We asked the questions of whether there is a cargo on the surface of the EV, is it inside the EV, or is it just loosely associated with it, and what is the degree of association? And then finally, I think there are a lot of people who are working on this question of the rarest of the golden snitches, right? So the EVs that are coming from tissues, because these EVs may be particularly important for our diagnostic approaches. They may also be very important for us to understand the biology of how we can move different EVs between compartments in the body. And so you may have heard about the L1 cam approach. So many people have used L1 cam, which is a surface marker, pull down EVs that may be coming from the central nervous system, specifically from neurons, or peripheral neurons for that matter. And so there was a session at ISEV 2021 about these molecules, these different approaches for enriching EVs from specific sources. So many things that are happening right now in EV characterization, including from blood. And if you're really excited about these methodologies, about these different platforms, the instruments, the technologies, do have a meeting that's coming up. So thank you all for attending today. I hope you'll also consider looking at this meeting that will be coming up in November in Honolulu. So this meeting is called ISEV X-Tech. It's the EV Methodology and Technology Summit, and the early registration deadline is actually next Friday. So you have plenty of time to take a look at the program there and see if you'd like to contribute and interact in person with some folks who are working on method development and technology development. So I will actually stop there and take any questions or attempt to take any questions that you might have. But thanks again.
Thank you, Ken. It was a really great run through of everything, everything about everything. So let's start the questions, if there are questions in the audience, and then in the meanwhile, I'll check the chat. I have a question. Tomorrow we will start at the workshop, also looking at the presentations here. And I know that from my group, Johanna Puutio will be discussing these different methodologies and how we would try to actually handle, isolate small EVs and exomeres with the technique from published by Zhang et al. And what we come up with, well, we discuss more tomorrow, but what we are puzzled with is that what technique would enable us to estimate the different subpopulations, the larger and the small, because it seems that everything is really biased. So what's your take on
mode? Here's the mode size, without also saying, and here is the range of sizes that this instrument can detect. And to determine that range, we also have to use a kind of particle that would be as similar as possible to what we're actually measuring. It's one thing to take a polystyrene particle, especially for an optical method where you have a lot of scatter from the polystyrene compared with that from the EV. And it's another thing to take some other let's say a liposome that would be much closer. Quite right that the range will be different for different platforms. And what would be wonderful would be to have a platform that would let us measure